So now that we've reviewed the properties of an exponential function, we're going to look at some application questions where we're interpreting what's happening based on a, b, and x. Okay, so just one more time, if b is positive or greater than 1, we have a growth. If it's between 0 and 1, we have a decay. And our a tells us the vertical stretch, which also tells us the y-intercept. So similar to yesterday, we're going to be using equations kind of like the financial equation where the amount is equal to the principal times 1 plus your interest, all to the power of the number of compound periods. And the number inside, 1 plus I, it's suggesting the growth factor or the decay factor. That's the only difference today. So yesterday we were talking about interest. Today, whatever's inside the brackets here, that's pretty much like our b. Okay? That's going to tell us what the growth or decay is. Why don't we try using the exponential function y equals a times b to the power of x in this example. So in 2012, the university population of a country was 160,000 and was increasing at an annual rate of 4.5%. Okay, if the function representing the population is of the form y equals a times b to the power of x, we're going to state the values of a and b. So one thing I didn't note earlier when we were talking about the base graph of y equals a times b to the power of x was what quadrants all these types of questions will be applicable in. Okay, so I'm just going to draw a quick example. Say this is your exponential function, and we're now talking about time. If my x-axis is the time, would I ever have negative time? No. So that quadrant's gone, that quadrant's gone. Okay, we'll never have negative time. Say this was talking about population, and that's my y-axis. Am I ever going to have negative 75 people? No. So this quadrant's gone, that quadrant's gone. Therefore, we're only looking at quadrant 1 for these types of questions. Okay, so if A is your y-intercept, and we're just looking in quadrant 1, we could basically describe A as the starting point, the initial value. So in this case, 160 was the initial population. That would be the y-intercept on your graph. Okay, now I've obviously drawn this way too low, but if I were to draw it accurately, you would have it like way up here. Okay, and it'd be at 160,000. Okay, that's our starting point, and then it's going to be growing exponentially. And I know it's growing because they said it's increasing at an annual rate of 4.5. Can I erase this? So A is always going to be your y-intercept, your vertical stretch factor, and in the case of growth and decay, it's going to be the number that you start at. It's the initial value. So A is 160,000 people. And B determines the growth or the decay. In this case, they're telling us we're increasing by 4.5%. So if we want to include that 160,000, we have to show that it was 100% of what we had plus 4.5%. Okay, so we have 104.5%. So our B value will be 1.045. Remember, if B is greater than 1, we have a growth. If it's between 0 and 1, we have a decay. And because we have a growth, it has to be 1 plus the 4.5%. So let's write an equation to represent the university population P of a country as a function of the number of years and since 2012. So we'll have population is equal to our initial population, so we'll have population at 0 time, multiplied by the growth factor, which is 1.045. Oh, and it's going to be to the power of n years. Anytime we're dealing with a question like part C where we have to find something, it's always good to just note what everything is. Okay, P0, that's pretty much like our A value, which we just found, 160,000. What's your N going to be? It started in 2012, we need to figure out the population in 2015. 3, good. Okay, so we can just plug into the equation and we'll figure out our population in 2015. So 160,000 multiplied by 1.045 to the power of 3. So help me out. What are you going to calculate? What do you get? 86.58. Okay, so let's talk about this number. In this lesson, there's going to be a lot of debate on what to round to. And the reason why is because of the context. So for example, here we're dealing with population. The general population is 182,586 or 87. Now if this was grade 6 and we were just doing regular rounding, okay, that 5 would bump up to 6 and we'd be at 587,000. Okay, but in this case, this 0.58, it's talking about a person. Can you have part of a person and just round up like, oh, I have half a person? Yeah, that's a full person. Technically, yes, there are some disabilities, but we're not going to get into that. Well, you're either a person or you're not, though, right? Like, if you're talking about physical being of a person, then we can get into disabilities. But you're a person or you're not alive, is what I'm getting at. So, can we round up to say that this is a person? No, it's actually 182,586 people. Okay, so I wasn't trying to be lacking sensitivity there at all. Okay, I just wanted to point out that you're either a person or you're not. So if the sorry, I'll just want to clarify. I've had people say comments like that in the past, so I just thought I'd address it up front. I'm not trying to be insensitive. Okay, so if the population continues to grow at this rate, determine the number of years to the nearest year for the population to double from its 2012 size. Okay, so we're going to continue growing at the same rate. We need to figure out how many years to the nearest year for the population to double from its 2002 size. What was the population in 2002? Or 2012, sorry? 160,000. Okay, so the final amount, which P is going to represent, will be 2 times that. And let's just leave it as 2 times that. You don't need to expand. It's going to be a waste of time, as you're going to see as we go through the steps. Okay, our growth rate, or our B, is 1.045, and our N is what we're going to be solving for. So plugging in, we get, let's just write the equation again. Okay, and sub in what we know. So the final population is 2 times 160,000. That's going to be equal to our initial population, 160,000, times 1.045 to the power of n. You want to isolate the base with the exponent. So we're going to divide by 160 first. And if you divide by 160 on this side, and divide by 160 on that side, they're both going to cancel out. So we get 2 equals 1.045 to the power of n. is there any way of getting the same base? No, so we have to use logarithms to solve this. So we can write log base 1.045 argument 2 is equal to n. You guys remember how to put that into your calculator? So change of base identity. We have log 2 divided by log 1.045, that equals n. What do we get? Okay, so with all the decimals, we get 15.75 and a few more things. But we need to round to the nearest year. So question, say this was like a, I'm just throwing this out there, say that was a 4, 5. Okay, in 15 years, would we have had a doubled population? No, so we've got to bump up to the next year. This one we're lucky because it had 7, 5, so it's a bit easier to think about. We would round to 16 whole years. Okay. So, because the other class really had lots of questions about rounding, I just want to emphasize, if they said to the nearest year, and we had 15.45, you would say 15 years. But if they said how many years, and it was either 15 or 16, then you would say 15 in the case of 15.45. Okay, but if they say to the nearest year, okay, that would round to 15 years. But if we're speaking contextually, then technically after 15 years, do we have double the population? No, so it would actually take, if we're talking about whole years, 16 years. Okay, so it just depends how they're asking it. If they say to the nearest year, you would say 15 years in this case. If they're asking contextually, it would actually have taken 16 years for it to double, not 15. Okay, so it's a bit tricky, but you just have to think about how they're asking it. Alright, the number of fish in a lake is decreasing by 5% each year. Growth or decay? Decay. So your B value will be between 0 and 1, right? Okay, there's just too much fishing, so they've decided, or they figured out that the number of fish are decreasing by 5%. So if the number of fish present is an exponential function of time, we're going to state the base of the exponential function. So at one point we had 100% of the fish in there, but now they've realized that 5% have been eaten, or they're out of the lake, so now we only have 95%. And as a decimal, we write that as 0.95. Again, if we have a decay, your number will be between 0 and 1. It's 100% of what you had minus the value they give you. So if we had to write an equation to show the number of fish that are present after t years, we're going to use n of 0 to represent the initial population, and n at a certain amount of time to represent the final population after t years. Okay, so n of t will equal n at 0 years, multiplied by the growth rate, decay rate, 0.95, to the power of t. And then they give us some information for part C. So if there were 2,500 fish present in 2012, how many would you expect to be present in 2017? So going from 2012 to 2017, how many years? 5. 5. So n is 5. Oh, sorry. T is 5. Okay. T represents the number of years. Okay, the initial fish, 2,500. And we've got to solve n after 5 years. A number of fish after 5 years. So with the formula above, let's just plug what we know. Okay, n of 5 is what we're solving for. We started with 2,500 fish. Our decay rate 0.95, and we're looking at 5 years. So this one's fairly straightforward. You're just plugging this into your calculator. And how many fish do we get?
1934.45.
Okay, can we have part of a fish?
No.
No, so we round to 1934 fish. Okay, part D. How many years would it take to the nearest 10th for the fish population to reduce to half of what it started with in 2012, which was 2,500. So this time, NT is going to be equal to half of the original population. And 0 is still 2,500. Okay, keep in mind the growth or decay rate stays the same. And we're looking for T in years. Okay, so we started again with n of t equals n at 0 times 0.95 to the power of t. So let's plug in what we know. After a certain amount of time, we're going to end up with half of the original population. We started with 2,500. The decay rate 0.95. We have to solve for t. So what's going to happen to the 2,500? Okay, divide by 2,500 on both sides. They cancel out. Then we get half, or 0.5 equals 0.95 to the power of t. Don't think we're going to get the same base, so in order to solve for the exponent, we have to use logarithms. Now just to remind you guys of another technique we could do. We could apply a logarithm on both sides. And then I could apply the power law. So I'm going to bring this exponent to the front as a coefficient. And then to solve for t, what do I have to do with log 0.95? Divide, yeah. So we get t is equal to log 0.5, or a half, divided by log 0.95. What are you guys getting there? 13.51. Alright, so they're telling us in this case we need to round to the nearest tenth. Now the other class we had a little bit of a debate on what to round to, because technically if we rounded down to 13.5 there isn't half of the amount. Okay? There's a little bit more because of that darn 0.1. So luckily the question is guiding us. They're just saying whatever answer you get, round to the nearest tenth. Okay, so it's not what in context would it be, it's what's your answer, round that to the nearest tenth. So we would have 13.5 years. Okay, so if it tells you to round to a certain amount, just round to that amount. Don't even think about it. Now this question here is dealing with the natural number, which is e. And I introduced briefly the ln button on your calculator, but I just want to review it with you in case you see a question like this in the future. Okay, so on your calculator, you guys find the log button, and right below it, you see ln. That's the ln button. Okay, we're going to answer this question using that button. So the intensity I0 of a light source is reduced to I after passing through d meters of fog. According to the formula, I equals I at 0 time, or distance, multiplied by e to the power of negative 0.12 times d. We have to figure out at what distance to the nearest hundredth of a meter will the intensity be reduced to 1/4 of its original value. So they're not giving us any original value, which means we leave that as the intensity at 0. They're telling us that the final intensity will be 1/4 of the original value. So our I is actually 1/4 of the original. So knowing that, we're just going to plug that into the formula. We get 1/4 of the original is equal to the original intensity times e to the power of negative 0.12 times d. Now, if I want to isolate our base e to the power of this, what do I do with the original intensities? We've done it 2 times. Pardon? How do I get rid of the I at 0 times for distance? Divide. And if I divide on this side, it's going to cancel out as well on that side. So we're left with 1/4 is equal to e to the power of negative 0.12 d.
What is e?
It's a natural number. We briefly touched on it in one of the lessons. It's a specific value that comes up a lot in higher level math courses, but it's considered an extension in Math 30. So I'm not going to get too much into it because it's very, very unlikely you're going to see it on your diploma. But just in case you do, I want to introduce how you would solve using your calculator. Okay. Pardon?
How do you know to put it there?
It was given.
Oh, it's like that.
Yeah.
But like if we ever needed it, it'd always be in the question.
Yeah, it would give the e in the question. Yeah. You'd never just magically make it up.
Yeah.
So here it was given in our formula. So let's just go with what we know. We know logarithms, right? There's no way we're going to get 1/4 to be the same as base e. So we're going to put this into logarithmic form, which you guys already know how to do. Okay, so we're going to go log base e of our argument 1/4. That's going to be equal to negative 0.12d. And like I said, we briefly went over this in one of the lessons. So I'm just going to make a note. If you say add logarithm base e to 7, okay, argument 7. In your calculator, you would press ln 7. Ln is the equivalent of log base e. So here, we could calculate ln 1/4. And then we have that equal to negative 0.12d. To get d by itself, what do I divide by? Good, you divide by negative 0.12. And that's going to give us our d value. And they're telling us to round to the nearest hundredth. Okay? So at what distance to the nearest hundredth of a meter would we have? So rounding, what do we get? Good. So just the main thing is if you ever see log base e, you can press ln and then the argument. Okay. So on the next page, it's basically developing a few formulas for how to get the half-life and the doubling time. But I'm going to skip that and just go right to the formula. Okay, similar to the questions we were just doing, A, that's going to be the final amount. So for example, we just looked at final population or final intensity. A0 will be our initial amount. Okay, so this is A at 0 time. C is going to be our constant, similar to how B was. You know how we had a decay or a growth? C is kind of like that factor. It's either a growth or decay factor. And it's going to be a constant, which would be representing 2 for your doubling time, 3 for tripling, and if you had a half-life, you would just put half in there. If you had a quarter life, your C would be a quarter. Okay. The way you're thinking about it is, okay, how does it compare to the original? So if it's doubling, 100% times 2 is 200%, and as a decimal, that's 2.0, right? So 2 would stand for doubling. Okay, that's your constant. It's like your growth or decay factor. Then we have 1 over p, which is the period of time for that doubling, tripling, or halving. So how long it takes to triple, or how long it takes to get a half of that amount. And then t is just the amount of time in total that we'd be talking about. Okay, we can rewrite this formula as such, because when you have a base raised to an exponent raised to another exponent, what do you do with the exponents? Multiply. So it's just a little bit easier to write your formula like this. Okay. Sometimes you might see it in function notation too, where they're talking about a specific amount of time, and t is just something. Alright, so a patient feeling ill had a sample of bacteria taken from her throat. The sample contained 387 cells. 24 hours later, the sample was recounted and was found to contain 8,012 cells. We need to find the doubling period of the bacteria to the nearest tenth of an hour. So let's just write out our formula again. The amount equals the initial amount times whether it's a doubling period or a tripling period or whatnot. In this case, we have a doubling period, to the power of t over p. I always like to start with the initial amount, so I'll just put A0 here. Okay, what's the initial amount? Good. 387. And what amount did it get to, the final amount, A? 8,012. Okay, they're telling us it's doubling. So what's our growth factor, C? 2. Good. Okay, and then this is where it's sometimes a bit tricky when they're telling us about time. Okay, they're saying 24 hours later, the sample was recounted and was found to be this amount. Okay, but then if we read further, it says find the doubling period. So P is actually what we're solving for. They ask for a period, you're solving for P. And if they're telling you the amount of time that it got to the final amount, that's your T. Okay, so T is 24. So given our knowns and our unknown, we just have to plug in itself. So our final amount was 8,012. Our initial amount was 387. We're doubling, and it's going to be to the power of 24 over P. We need to solve for P. So first thing we want to do is divide by our initial amount. So we end up on the left side with 8,012 divided by 387. And hopefully you guys know this, but I'm just going to state it really clearly. Never round your final your answers for your calculations until the very end. So, in fact, I would just leave this as a fraction until you finally calculate it at the end. Okay, so 8,012 divided by 387 will equal 2 to the power of 24 over p. Do you think there's any way we can get 8,012 divided by 387 to be a base 2? No, so we have to use our logarithms. And you can apply a log to both sides, or you can just change it to logarithmic form. Okay, I'm just going to change it to logs. So log base 2, argument 8,012 over 387 is equal to 24 over p. Now before I go to solve this any further, I'm just going to do a real quick example on rearranging equations. So say I had a equals b divided by c, and my goal was to solve for c. It's in the denominator. So I would have to multiply both sides by c first, because I can't solve for anything in the denominator, so that would cancel out. Then I have c times a equals b. Again, my goal is to solve for c. So I need to now divide by a. That cancels out here, that cancels out here. So at last I get c equals b over a. If we look at what we started with, a equals b divided by c, what has happened to the a and the c? They switch places. So rather than having to do this every time, can we not just switch this entire logarithm with the p? Makes it a little bit easier. So let's do that. That's an error. Okay, so we get p equals 24 divided by logarithm 8,012 divided by 387 with a base of 2. Can we change the identity to change the base to base 10 and just go, you guys remember this? Hi, Stan. So we can change it to log 8,012 divided by 387 divided by log 2. You guys remember that? So this is the change of base identity, where you're changing both bases to 10, and you're able to divide them. So our final calculation will be 24 divided by log 8,012 divided by log 2. And if I were you, I'd probably just calculate the denominator first, press enter, and then go 24 divided by second to answer. Then it carries all your decimals. So we need to find the doubling period to the nearest tenth of an hour. And if we round up, we should get 5.5 hours. Okay, the answer is 5.489. If we round, we get 5.5. So a lot of these questions, they tend to be similar, but the one thing that's different in this next question is we're going to be solving for t, so it's in the numerator of that exponent. Okay, so in April 1986, the nuclear accident at Chernobyl contaminated the atmosphere with quantities of radioactive iodine-131. Okay, the half-life of radioactive iodine-131 is 8.1 days. Determine the number of days to the nearest day it took for the level of radiation to reduce to 2% of the original level. Did they tell us the original level? Nope. So A0 is just A0. Did they tell us the final amount? Okay, it's 2% of the original amount. So we have 0.02 times our original amount. Okay, there is a half-life. So what is your constant? It's going to be a half. Okay, and then they're telling us that the half-life itself took 8.1 days. That's going to be our P. Okay, for just the half-life, it's 8.1 days, not the whole amount of time. So P is equal to 8.1. And our goal is to solve for T. Okay, determine the number of days from nearest day it took for the level of radiation to reduce to 2% of the original. If you were to read through this question again, this first sentence is information about the scenario, but it has nothing to do with information to help us with the formula. So with word problems, you need to be able to dissect what's important and what's not. So let's just plug in the important information into our formula. We'll write that out again. Okay, our initial amount is 0.02 times our final amount is 2% of the original amount. That equals our original amount times the constant, which is half. If you want, you can put 0.5 to the power of T over our half-life period, 8.1 days. So we've done this type of question a few times. Bruce, what's my first step? Okay, you have to solve for T. What are you going to divide by?
What is it? 0.5.
I'll ask Jackson how about.
I think it was A0.
Yeah, good. So we're trying to isolate this exponent. Okay, first?
Yeah.
Trying to isolate this. So we have to divide by the initial amount. If we do that on one side, cancels out. We also have to do it on the other side, and that also cancels out. Now we have 0.02 equals 0.5 to the power of T over 8.1. Again, we don't have any chance of getting a common base to solve for the exponents, so we have to use logarithms. Okay, so we have log of our base 0.5 of our argument 0.02 equals T over 8.1. Using the change of base identity, I'm going to write log base 0.5 argument 0.02 as log 0.02 over log 0.5. That equals T over 81 or 8.1. To solve for T, what do I do with the 8.1? Good, I'm going to multiply it on both sides, and we get our T. So let's put in log 0.02 divided by log 0.5, figure out what that is, then multiply by 8.1. So you get 45.715 and a bunch of decimals. They're asking us to round to the nearest day. Okay, so that would be 46 days. Truthfully, the last question is fairly straightforward, and we've done questions like this now. So I'm just going to do one part of that question that maybe you wouldn't have thought of, but the rest of it's pretty much the same. Everyone finished? Copy? we're still gonna read through the question, and I'm just gonna talk about basically part B. Okay, so we're given the formula where our constant is a half-life, because they tell us the radioactive isotope has a half-life of 7 years. So our constant's half, and if the half-life is 7 years, that means our P is 7. Okay, and they're telling us to determine how much of the isotope must be initially be present to decay to 60 grams in 14 years. So I'm just going to write out the formula for you. We're going to end up with 60 grams. Our initial amount was unknown. Our constant, or our decay factor, was a half-life, so we have a half as our B value. Okay, the time was 14 years, and the period of the half-life was 7. So you could go ahead and solve. You'd get that the initial amount was 240.
Where's the seven?
Yeah, which means seven.
Right there.
Oh,
So they told us that the half-life was 7 years, so that's our P. Okay. So if we solved for 8, 0, it would basically be 60 divided by half to the power of 2. Okay, so we'd be going 60 divided by 1/4. And we get 240. The part that I wanted to talk about was part B. They're saying, write an equivalent formula where now C is 2. We still have a half-life, but they want, instead of this to be a half in the constant space, they want us to write it as a 2. So tell me, how can I make it so that these two statements are equal? 2 to the power of negative 1. Brilliant. So our formula would just be this. Whoops, 2 to the power of negative 14 over 7. Okay, or you could write it as to the power of negative 1 to the power of 14 over 7. That's all it's asking for. So if you're ever asked a question, how can you change the base, just remember that negative exponent law. Clearly we're not doing lesson 4 today. We're just doing lesson 3. Everyone should at this time have a portfolio. If you don't, we'll make sure you get one.